In this video, we'll be talking about modern CPUs and all of the optimization tricks that they use to help run your code as quickly as possible. So let's start by diving into a very simple code example. So here I have a very simple Julia function that just adds together two vectors a and b based on an order specified by another array that I've called indices. So let's create some small test arrays to see what this function does. And you can see it performs the exact same task as if you were to just do a.add b. The function also gives you the same result if you reverse the order of the indices. Instead of going in order linearly, you go in reverse order instead. You can see all of these give you the same result. But let's benchmark this function for much larger inputs. So let's create two arrays with over 8,000 elements. So let's create another array which stores the indices from 1 to n. This collect function is just a convenient syntax to do that. So let's just check that our function works the way that we expect, and it gives the right answer. But now let's run a benchmark on this function, and we'll use the @benchmark macro from the benchmark tools package. If you haven't installed the benchmark tools package, watch the previous video first. So we can use this syntax to run the vector add function with the inputs a, b, and c, and remember we're using the $ here to interpolate these variables into your benchmark to make it a little bit more accurate. And in this video, let's just focus on the minimum time taken, which is around 4 microseconds in this example. So now let's see what happens to our benchmark when we change the order in which the elements are added together. In order to shuffle the array, we'll need to use the random package that's in the base library. So we'll say using random, and we'll create this new array, shuffled indices. Let's just do a sanity check to make sure that our function still returns the correct result. And it does. Let's just peek inside the shuffled array to look at the first 10 elements. And you'll see that the order in which the elements are added is completely random. So now that we have the shuffled array, let's benchmark the same function with our shuffled values. Before we run this function, make a prediction on what you think will happen to the performance after we've shuffled these indices. Do you think it should stay the same, or do you think it will be faster or slower? Pause the video now if you want some time to think about it. And you can see that we have very different results here. Before we had around 4 microseconds for the fastest time, but now the fastest time is around 10 to 11 microseconds instead. So shuffling our indices here degraded our performance and resulted in the runtime being more than doubled. Now this should be a kind of surprising result. We're running the same function with the same input types, so all we've done is change the order in which the elements from A and B are loaded and added together and stored into array C. So let's try and get to the bottom of why this performance difference occurred. So one thing that we can rule out straight away is making sure that the code is actually running the same instructions for both inputs. So I've written this quick function that will create our input arrays and write the machine code to a file using the code native function from the interactive utils. So let's run this function and have a look at the machine code. So now that we've run this code, we can see 2 new files have been generated. We could go through this file manually and check for differences, or we can use VS Code to highlight the differences between these files. So if you select the file in the File Explorer and right click and click Select for Compare, click the other file and select Compare with Selected, we should be able to see the differences highlighted. Looking through these changes, you can see that the bulk of the machine code is actually unchanged, and they're performing the exact same operations. The only thing that is slightly different are the names of the functions that are being referenced throughout this machine code. This has no functional difference on the actual performance of the code itself. So now that we know that the machine code is the same, we need to come up with another explanation for why the performance is different between these two inputs. Why should it matter to the computer which order you iterate through an array? This can't be explained by our simple von Neumann architecture that we introduced at the beginning of this course, and so we need to add to our mental model to be able to describe this effect. This is what we'll talk about for the rest of this video. So let's think back to our earlier video on the von Neumann architecture. One key feature of this architecture was the separation of memory from the registers of the CPU. The CPU needs to request data from memory to be able to function. However, we missed one key fact that is relevant when trying to describe these modern systems. In that video, we did not talk much about the speed of each operation relative to one another. In a modern machine, RAM, which is where the main memory is stored, is typically a few orders of magnitude slower to access than the registers inside the CPU. When the CPU requests data from memory, it has to wait many cycles for that data to become available and then sent over to the CPU. This latency between memory and the CPU is a huge bottleneck that would absolutely cripple the CPU's performance, as it needs the data stored in memory to be useful. CPU manufacturers address this imbalance by adding an intermediate layer between the CPU and the memory, and this is just a cache. This cache usually sits directly on the processor chip itself, but in this diagram we imagine it sitting in between the CPU and memory. To better visualize how the cache operates, let's simplify our diagram and focus on just the requests that the CPU makes to memory for certain pieces of data. I've also simplified the memory addresses to just be simple shapes and colors instead of binary data. Each shape and color combination represent a unique address in memory. So let's go through a simple example and see how the cache works. To start with, the CPU requests some data from memory, identified by a shape and a color which represents that address in the desired part of memory. The first place that the CPU checks for this data is in the cache. But in this example, our cache is empty and so it doesn't contain the data that we need. We call this a cache miss, and we are forced to go to memory to look for the data instead. Once that piece of data is loaded, it doesn't go directly back into the CPU, but instead it goes into the cache itself. Once the requested data is in the cache, it can then be copied into the CPU and used directly. The CPU will then move on to its next request, which in this case is the blue diamond piece of memory. Again, the first place that is checked is the CPU cache. In this example, this data doesn't exist in the cache, so we have to go out to memory again. Once loaded from memory, this is stored inside the cache as well, and then transferred back to the CPU for processing. So far, introducing the cache has had no real benefit to performance, but let's say that the CPU then requests the blue triangle again from memory. Now when the CPU checks the cache, it sees that it already has a copy of the memory stored there and uses it directly, instead of having to reach all the way out to memory. We call this a cache hit, and it can save an enormous amount of clock cycles as the CPU can continue processing without having to wait for the slow memory unit to look up the data. Now you may be asking, why do we even use a separate memory unit that is slow compared to the CPU? Why don't we just load everything into the cache? Well, the CPU cache has a very limited capacity to store data, as it's very expensive to manufacture. Main memory is usually stored on RAM chips that use a technology like DDR4 or DDR5. These technologies offer a much higher capacity to be stored at a much lower cost, but the cost of this higher capacity is a higher latency to access the memory, which is why we have this separation. So now that we've said the cache is a limited capacity, what actually happens when it gets full? Let's say that the CPU requests a different item and it's not found in the cache, so the data is directly copied from memory. This data should go into the cache, but if it's at capacity, then the data must choose a strategy to evict some data that's stored in the cache to make room for the new data. The exact strategy depends on the manufacturer. One typical strategy is to evict the least recently used element, and this means that the cache will usually have access to the most recently used pieces of data. The data that is evicted is overwritten with the new data that's loaded from RAM. If you structure your program so that frequently accessed data is in the same place, it's very likely that it will end up in the cache. However, this doesn't really explain our earlier example, so let's head back over to VS Code to have a look. So in our simple example before, we iterated over our arrays A and B in the order specified by the indices. But you can see here that the indices are unique. We're not reusing the same piece of memory twice. This means that the strategy of caching frequently used data does not actually help the speed up here, so it must be a different factor. So one other access pattern that's very common in programs is to access memory linearly. So for example, if a program is executing instructions, then it's very likely that the next instruction is the one stored directly after in memory. So what can CPU manufacturers do to try and take advantage of this memory access pattern? Well, since memory requests have such a long latency, why don't we just request a bulk of data so that several memory addresses can be loaded in one go, instead of waiting for each address to be loaded sequentially? We design our systems so that this bulk request is at typically similar speed to that of just requesting a single piece of memory. So let's say, for example, that the CPU is requesting the green triangle from memory. Our spatial heuristic would suggest that it's likely that the CPU will need the next few addresses in memory, and so we load all of them at the same time. This entire line of data is put inside the cache, and we call this chunk a cache line. Our heuristic pans out if the CPU needs the next few addresses because it's already in the cache when it's requested. And so in this example, we get many more cache hits, even though the data hasn't been requested before. This is the reason for our performance difference in the first example. The memory access pattern that we specified was more cache-friendly because of this spatial heuristic. When we loaded the first elements of each array into the cache, the CPU preemptively loaded the next few elements into the cache as well. So on the next run round, when we're requesting A2 and B2, these elements already exist within the cache line that was loaded on the first request. And so the CPU doesn't have to pay the cost to retrieve these pieces of data. When we shuffled this indices array, we got in the way of the CPU's heuristics for putting items in the cache. This caused a significant amount of cache misses, as we are essentially randomly accessing the elements in the array, and this can't really be accounted for by any sophisticated CPU heuristics. We'll talk again about these heuristics when we start talking about multi-dimensional arrays later on in this course. As you may have guessed, throughout this video we've kind of simplified this idea of cache. There's actually a lot that goes on behind the scenes to make this work, but one key aspect that we left out is how this cache is actually structured on the CPU. So what I've been referring to as the cache here is actually 3 distinct layers of cache called L1, L2, and L3 cache. Each of these layers still reside within the processor itself, but they are arranged hierarchically. So let's look at each of these levels and put some ballpark numbers on their size and the latency to access data within. For context, let's start at the CPU core itself. This contains the typical registers that we've seen before and the circuitry needed to perform the control and logic operations. There are a relatively small amount of these registers, but these registers themselves can usually be accessed within a single CPU clock cycle. If the CPU doesn't contain data within one of its registers, it can look up data starting with the L1 cache. Now if you have a multi-core CPU, each CPU core will typically have its own L1 cache that's dedicated for use within that core. The amount of cache available on the L1 cache varies depending on the processor, but typically this is in the range of 32 to 128 kilobytes of storage. The CPU can access the data from within the L1 cache typically within around 5 cycles. If the data cannot be found within the L1 cache, then the CPU will try to look it up in the L2 cache. This cache is already much higher capacity than the L1 cache, going up to a few megabytes per core on some chips. While a few megabytes also doesn't seem like that much, it's enough to store around 250,000 numbers. This higher capacity comes at a bit of a cost, since the latency for accessing the data here is around 10 to 20 CPU clock cycles. If the data is found here, it will trickle down into the CPU, so the data read from the L2 cache will be put inside the L1 cache before it's available on the CPU. How the L2 cache works depends entirely on the CPU architecture. If you're on a multi-core system, the L2 cache is typically shared by one or more cores, but on some architectures, the L2 cache is not actually shared between the CPU cores and it's just a second layer on top of the L1 cache that is available per core. But since some CPUs share this L2 cache, this has huge implications for parallel computing that we'll discuss later on in this course. If the requested data is not within the L2 cache, there's one final cache to check, which is the L3 cache. This is typically the largest cache overall, with some higher end chips boasting up to around 100 megabytes of capacity. This capacity is usually shared between all cores on the chip, and higher core CPUs will have higher amounts of cache to compensate. This cache typically has the largest latency cost, with data being available within around 40 to 70 CPU cycles. Finally, if the data is not found within the CPU, we have to reach out to memory. Here we're typically paying a cost of a few hundred CPU cycles to get the data. However, we have access to a lot more capacity. Even consumer desktop machines tend to have tens of gigabytes of RAM and are capable of storing absolutely huge amounts of data in this volatile memory. What we haven't shown on this diagram is permanent data storage that is backed by your hard disk or solid state drive. The data stored within your cache or memory is volatile, which means it's lost when the machine is turned off. Hard disks and SSD are permanent storage, which means that they can store the data even when they're unpowered. They are typically much higher capacity, but they are much slower to access for the CPU. In our example of memory, it took a few hundred cycles to access something from RAM, but if you're accessing something from an SSD, you're looking at a few 100,000 cycles. And if you're trying to access data from a spinning disk drive, this usually takes a few million cycles. Due to this tremendous difference in speed, CPUs typically perform these I/O operations asynchronously, so they can get on with other processing work without having to wait for a response from the SSD or hard disk. This is why it's often recommended to avoid excessive disk usage during the execution of your code, as it will likely bottleneck your CPU. So now that we have some idea of how the CPU's cache works and the relative memory access speeds, let's talk about the speeds of some other operations on the CPU. I'm going to be relying on this infographic from ithair.com. I've left a link in the description to the accompanying blog post for this infographic, and it's well worth a read if you're interested. This infographic was created in 2016, so some of the information may be slightly out of date, but it's useful to know what types of operations the CPU does and their relative speeds. Let's just pick a few operations to have a look at. The first is simple register-to-register operations. These are things like additions or bitwise OR comparisons. These happen in around 1 CPU cycle, and they're pretty much the fastest thing that the CPU can do. The next item on the list might be kind of surprising considering what we've spoken about today, and this is a memory write. And so a memory write can happen in around 1 CPU cycle because the data is sent out asynchronously and then the CPU will continue on with other tasks instead of waiting for the memory to actually be written. In some architectures, this memory might be written directly to the cache and not actually make its way into main memory for many cycles. The next kind of operations that I want to focus on are branching operations. So here we have 2 different entries, each with very different speeds. So the first of these is the write branch of an if statement. And so when a CPU executes, it does something called branch prediction. This means that it guesses which side of an if statement will be executed before it's actually evaluated the condition, and it starts evaluating that branch straight away instead of waiting for the condition to evaluate first. If the CPU is able to predict correctly, this only costs 1 or 2 CPU cycles. If the CPU makes a mistake in its prediction and the wrong branch is chosen, it has to reverse all of the work that it started doing and continue from an earlier state. This misprediction costs a lot more CPU cycles. Now let's take a quick look at branching in a code example. In this example, I have 2 functions that do the exact same operation. The only differences between these functions lies within the loop body itself. In the first function, we use an if statement, and in the second operation, we avoid this branching statement by directly converting the logical condition into a number and adding that into our count. Both of these functions will calculate the number of elements that are greater than 50 in an array. So given what we've seen in the diagram, you would expect that the branchless version should execute much faster because it can't mispredict a branch. And instead we're doing simple operations like logical comparisons and additions, which happen within 1 or 2 CPU cycles. I ran benchmarks for both of these functions with the same input, where the elements should be randomly distributed between 1 and 100, which means that roughly half of the time the if statement should evaluate to true. And you would expect there to be a performance difference here, but actually you can see that the performance of the 2 functions is essentially identical. The main reason for this performance difference is the Julia compiler itself, because it has optimized away the if statement in the first implementation so that the machine code for both implementations looks the same. Just like in previous videos, what we can do is use the code native function to print out the machine code for each of these implementations and compare them. If we compare the output from both of these, you can see that the only difference is in the name of the functions themselves. The actual operations themselves are identical from both files. This means that the Julia compiler is smart enough to optimize your code, and so feel free to use branching if statements in your code, because it's very likely that the compiler will optimize these away. However, you might want to keep this branchless programming in mind, especially if you're not programming in Julia. In other languages, writing your code, like in the second example, may end up actually being faster than in the first example. It really depends on how the code is compiled. So let's go back to our CPU operations. So next of all, I want to focus on the simple arithmetic operations in the CPU. You can see here that there's a clear hierarchy distinguishing different types of operations. The fastest type of operations are simple operations like add, or logic operations like or and. And then we have some other operations such as floating point addition, which costs a little bit more than doing simple integer addition because it's a little bit more complicated. You'll also notice that multiplication tends to be more expensive than addition. This will vary depending on the exact data type and the exact CPU architecture that you're using, but in general, the more complicated the underlying operation, the more complicated the hardware has to be to deal with this, and the less quick it will end up being. But the relative speed of these operations really depends on the specific architecture that you're using. But one thing that is quite common is that floating point division tends to be much slower than multiplication or addition. So let's have a look at an example of this in action. So here I have 2 functions that perform the same operation. What these functions do is take an output array and fill it with a vector that's similar to the input array, but normalized so that the sum equals 1. So for example, if we have the vector 1, 2, 3, and we want to fill a vector b with the normalized version of a, this function normalizes the output by dividing the element by the sum of all of the elements. And so in this case, it divides each element by 6. Equivalently, we could have written this operation by multiplying by 1 over 6 instead of dividing by 6. You can see that in both cases, these give essentially the same results, but due to floating point arithmetic, you might get something slightly different in both cases. While these 2 functions are basically the same, they have very different performance implications. Let's create vectors with 1,000,000 elements and benchmark both of our functions. And here are the results. You can see that the implementation that used the divide was actually much slower than the implementation that used the multiply, even though they are essentially the same algorithm. In this specific example, changing one character got our runtime from around 480 microseconds down to around 320 microseconds, so that's around a 25% speed up. You can also check to see that the output of these two functions are approximately equal to one another, but you should remember that you'll get slightly different answers up to some floating point rounding errors. So you can see that they're not exactly equal to one another, but they are approximately equal to one another. Now I want to draw your attention to some interesting parts of the CPU operations. You can see that some of these operations list vector addition, vector multiplication, and vector division. So in these contexts, what does vector actually mean? And it's referring to a type of operation called SIMD, which stands for single instruction, multiple data. And this is essentially a type of hardware parallelism where if you're doing the same operation on independent bits of data, you can group that into a single instruction and operate on all of these bits of data at the same time. In order to demonstrate this a little bit more effectively, I've made a small animation to show you how this works. To be able to perform SIMD, your CPU usually has to have special registers equipped to handle this type of operation. So imagine you had a wider register than the ones that we've been looking at. In this case, this register would be 16 bits wide. What we can do is split this wider register into 4 segments and store a number in each of these 4 blocks. So the first 4 bits in this case could store the number 7, the next few bits could store the number 2, and then 5, and then 3. Obviously in this example we're only using a 16-bit wide register, but some CPUs have registers that are up to 512 bits, and can store many more numbers with higher precision. Once this is in the CPU, you can load another vector of numbers into a different register, and perform an operation on them, for example addition. And this addition will work pairwise, so each different color will be treated as independent operations. And so we go through each column at a time and add the numbers together. What's important to note is that these operations will happen in parallel. These type of operations will still only occur on a single CPU core, but they're examples of hardware-backed parallelism. You can find out whether your CPU supports these type of instructions by going to its spec sheet. This is the spec sheet for my processor, which is an Intel i9. If you scroll down, you want to find an entry that lists instruction sets. As you can see, mine is at the bottom, and this is a 64-bit instruction set with some extensions. The extensions that are supported are SSE 4.1, SSE 4.2, and AVX2. If we check the Wikipedia article, SSE stands for Streaming SIMD Extensions, and these are the older basic extensions that a lot of modern CPUs will have access to. If we check the specific one that my CPU supports, which is SSE4, you can see that there are registers that are 128 bits wide, which can support up to 4 32-bit integers or 4 32-bit single precision floating point numbers. Some of the operations that you can support with these are element-wise multiplication or addition. You'll also notice that my CPU supported AVX2, and these stand for Advanced Vector Extensions. And in this edition, the registers are increased to 256 bits, which essentially means that we can store twice as many numbers inside these single registers, and effectively do element-wise operations in parallel. So let's see how we can use these operations within Julia itself. For this, I've prepared a function that calculates the dot product between two vectors a and b. By default, Julia will use SIMD operations if your CPU has them available, and it's allowed to do so. One of the main restrictions on this optimization is that it's not allowed to reorder your operations. Here we're performing a reduction, and for floating point numbers, this operation is not associative, which means we're not free to rearrange the order in which we add the elements inside. Instead, we can signal to the compiler that we're okay with them rearranging certain operations. In particular, we can use this @SIMD macro. This macro signals to the compiler that we're okay with it rearranging our inner for loop. Note that when you use this, you're telling the compiler that something is true. If it's not okay for you to rearrange these operations inside, then it's likely that the code produced won't give you the correct answer. You can see that if we use this function, we get an answer that is very similar to the one that we had before, but is slightly off up to some rounding point error. So now let's check to see whether this has actually sped up our code or not. And you can see here that there's a significant speed up. Before, the minimum time was around 370 microseconds, but this has been reduced to 78 microseconds. So you can see this is around a 4.75 speed increase. What's nice about Julia is that we can inspect the low-level code generated to see what's actually going on here. When I'm checking for SIMD instructions, I quite like using the LLVM instructions because it's very clear what's actually going on without reading the native machine code. This function has a lot of instructions, but let's scroll up to find something interesting. So here you can see quite a few instructions that list this 8x float. This means that it's using registers that store 8 32-bit floating point numbers. In total, this is 256 bits, which is the maximum register size for my particular CPU. And now you may be asking, why didn't we get an 8 times speedup? We only got a 4 times speedup. And the main reason for this is memory bandwidth, because in our function, in each operation, we have to load from 2 elements of an array. If we instead write a new function that sums over every element in a single array, this should reduce the memory bandwidth of our function, and therefore we should be able to see the speedup of SIMD much more effectively. If we benchmark these 2 different implementations, one using the SIMD macro and one without, you can see that the speedup here goes from around 370 microseconds to around 40 microseconds. And so here we actually improve past the 8 times speedup that we were expecting, and instead reach 9 times speedup. However, if we check the speedup in the mean case, you can see that this is only around 7.5 times speedup. And in this case, we were able to achieve this increased speedup because we reduced the memory bandwidth by not loading from the other array. As a quick rule of thumb, we can estimate the memory bandwidth required for the my.dot function. In our case, we looped over 10 to the 6 elements and performed 2 loads for each of these iterations. In our case, we were using 32-bit numbers, which are 4 bytes worth of memory. Instead of giving our answer in bytes, we can give our answer in gigabytes instead. And then we divide by the time taken to perform the operation. On average, this was around 100 microseconds. And the operation here tells us that the memory bandwidth used for this function was around 75 gigabytes per second. Now this is just an estimate, it's not an official number, but this is very close to the total memory bandwidth that I've measured on my machine. And this is the main reason why we only saw a speedup of around 4 times, because we got bottlenecked by the memory bandwidth on our machine. As this is a high-performance computing module, I thought I'd hop onto our local cluster and show you what much more powerful CPUs are capable of when you enable these SIMD instructions. So here I've opened up a terminal on our local cluster. Now this machine runs on Linux, and in the terminal you can use the command ls-cpu to have a look at the specs of the processor contained within. Now this has quite a lot of output, but what you're looking for is the flags. Now it's quite hard to see within this, but you can see that there are certain flags called AVX512. And as the name implied, these are 512-bit extensions to the SIMD programming paradigm. This means that in theory, we should be able to do twice as many operations as on my local CPU. So what we'll do is copy in our functions from before that calculate the dot product. And again, we'll generate 2 arrays with 1,000,000 elements each. And remember that we're using 32-bit floating point numbers. Now we can run the benchmark for this dot product function. And in this case, we went from 790 microseconds down to 77 microseconds, which is around a 10 times speedup. Now again, this is memory bottlenecked, and we can check that by looking at the specific instructions that were compiled for our SIMD version of our code. Again, we use the @code LLVM macro to have a look at the LLVM instructions that are generated. Now we have to scroll up quite a bit to have a look for the vector instructions that are being used. You can see here that the floating point operations used use 16 individual floating point operations at a time, stored within a single 512-bit register. And so in theory, SIMD should be able to speed up our operations by a factor of 16. Now let's benchmark our custom sum functions, which have a reduced demand on the memory bandwidth, and so we should be able to see the maximum speedup from the SIMD instructions. And you can see here that the speedup is a little bit more dramatic. We went from around 800 microseconds down to around 40 microseconds. And so this is roughly a 20 times speedup, which is much closer to our 16 times speedup that we expected. One reason that we get a better than expected performance here is that we need fewer instructions to actually execute our loop. And this is because we're adding up 16 elements in a single instruction, instead of having to have multiple instructions to load each of the 16 elements and then multiple instructions required to add these together. So not only are we doing our operations in parallel, but we're actually reducing the overall instructions that are needed around this loop as well. Additionally, there are some other speedups that the @simd macro will inject into your code that allows the code to speed up by a small fraction. But in general, you can gain a massive speedup from using these SIMD instructions, especially when you deploy on HPC systems that are more likely to have CPUs that support AVX 512. And that's where I'll end this video. If you found these topics interesting, I've left a link to 2 more videos in the description that go into these topics in greater detail if you're interested in learning more. Over the next few videos, we'll be talking more about optimization techniques and trying to get the best performance out of the code that you write.